Hello, and welcome to a special episode of Machine Learning where I have a bloody nose. So I guess the pollen got to me. I think it's pollen because nobody punched me. It's just that there's a lot of pollen in the air right now, and I ran out of Kleenexes, unfortunately, at a bad time. So sorry, I'll be lecturing with toilet paper hanging out of my nose. I know that's weird and embarrassing, but better than bleeding all over the place and dying. So there we go. Let's see. We are very near the end because this is today, and the end is right there, which is 1 week from today. Technically, I'm not supposed to accept any assignments after the last day of class, unless you've made special arrangements with me. If you need to, go ahead and let me know. Otherwise, I think we'll wrap it up. One thing I didn't do last time is talk much about assignment 6, so let me just start by asking, how is it going? Does anybody have any follow-up questions? Now, most of the class has already done it, so this is far too late, and I apologize, but should we do a lessons learned and things like that, and any debugging help you want to give the few people that are still struggling with it? Anybody want to say anything about this assignment, or, yeah? Yeah, I kind of didn't realize until after the fact. Writing in a PNG format is not some kind of requirement. It's totally okay if you want to turn this assignment in SVG form or something else. I just thought writing a PNG file would be the easiest solution, and I'm sorry for those of you to whom that caused a technical hurdle. I think I did mention at one point that it was okay to just output data and plot it in Excel. Anybody hear that? Okay. But, hey, you learned a useful software engineering skill that has nothing to do with machine learning, I guess. Do you want me to talk about PNG files, or I guess you're already past that point now? Maybe just for the future, add a note to this that says there are other options. Is that what you're getting at? Okay. And if you make it 0 by default, everything's transparent and you can't see it.
Yes, and I was weird because in Windows, I would click on my image and I was seeing the preview, and you guys have transparency capabilities. I was seeing my image and I'm like, oh, it's there, and then I open it and there's nothing there. And I was like, the thumbnail is right, but when I open it, there's nothing there. And yeah, there's a little bit of time, but yeah, you just delete the A and then it's not transparent.
Well, if it makes a difference, I feel for you, because I remember having that very same experience, and learning to work with images was painful for me as well, and you're a better man for it, I guess. Sorry, that's so insulting. I'm sorry. But yeah, I guess you just got to go through that. I think you found that buffered image is the name of the image class you need to use in Java, right? Because if you use a regular image, you actually can't write to the pixels, but buffered image you can. C++ is way easier if you use Linux, because I provided code that should just work, and all you have to do is apt-get install libpung.lib or something like that. If you use Windows, however, PNG on C++ is very difficult. Anybody else face that? The main reason it's difficult is you have to rebuild libpng, and you have to get the 64 or 32-bit version right, and a bunch of other stuff. At least that's what I found. I know a couple of you actually used just the SVG maker back from assignment 2 or 3. Must have been 3. And if you build an image using a bunch of rectangles for pixels in SVG format, you can make a great big image that's not extraordinarily large. But that's a terrible way to make an image, right? It's way more bloated than other image formats. But for this assignment, it would be fine. Yeah. So, sorry about images, but it's really good to be able to make images, because that's a power. Visualizing your code is a powerful technique for knowing what's going on. So I don't feel too bad. Yeah.
Python imaging library also really
Ah, cool. Okay. How about running time? So on mine, I think this ran for 10 minutes. How long did yours take to do the unsupervised training of all those images? Anybody get it down to about 10 minutes? Cool. Good job. 1,000 seconds? I don't even comprehend what that means. 15 minutes. Okay. That's pretty good. Anybody take several hours and have to run for a long time? Okay, sorry. Python? Okay. That happens every year as Python users find this problem is really cumbersome. I don't know why, because NumPy, however you pronounce that, is supposed to make it super fast, it's supposed to be well optimized, but for some reason this assignment burns people every year. And I kind of warned you at the start, but I don't know why. One year I had somebody do this assignment in MATLAB. It took her like 3 days to produce the image, but she got valid results. It was awesome. So apparently you can do it in MATLAB too. I don't recommend it. Yeah.
You want to do this on a bigger picture, like a bigger size image? Would you want to make output more pixels, or would you want to just increase the size more?
Yeah, good question. So in theory, while these are 64 by 48 pixel images, which are crazy tiny, in fact, the ones you're looking at are higher resolution than that, just because I could. No matter how huge you made the image, it's actually, the size of the image would make absolutely no difference, because it's really the complexity of the content of the image. So I like to think that while certainly there are more complex images than this, you could only get to a certain degree of complexity while still being a real-world problem. Meaning, nobody's going to do Where's Waldo with one of these problems, right? You're going to do, maybe a crane with a background and a factory thing going around and a cat that keeps running by or something. But you're never going to have a scene that's just so extraordinarily complex that you've got to fit a bunch of things about it. That didn't come out well. But my point is, I'd like to think this could just be an arbitrarily high-resolution image, and if you're just randomly picking pixels, it'll still take the same number of pixels to produce a meaningful internal representation. Therefore, we've kind of waved away the whole concept of what resolution can it support, and now we're asking the question of what level of system complexity can it support, which I think is a lot more interesting of a problem, because now we're learning, how much can we actually look at the world and understand what's going on in it? And is that not the problem humans are just amazing at? I like to think that this, for some reason, machine learning heavily studies supervised learning, mostly because it's easy to comprehend. But that's not what humans do a lot of. We do a whole lot of this type of thing, where we look at stuff and understand it. And I feel like that's the crux of our capabilities as human beings. Which is why I like to end with this assignment, is it shows you that, hey, these models you've learned how to train can actually be used in different ways, not just supervised learning. And I think you guys now have a pretty good understanding of unsupervised learning and why it's important, right? Because you get, actually, I'm not sure I said this. If I didn't, I should have. Do you get why we had to reduce these down to 2 dimensions? Yeah, there are 2 degrees of freedom. But let's ask the question, what if we didn't? So here's a transition function, here's an observation function, here's state, which I think I called V for some reason, and I called the observation X, and the control's U, because you use the common letter for control signals in a lot of control systems. And we built this. And there are approximately 9,000 pixels in X. Anybody remember the exact number? 64 times 48 times 3, whatever that is. What if the size of V or say 64 times 48 times 3. Then this observation function could basically be identity if we wanted to. There's no real job being done here. And then this whole system, in fact, we could just wave this thing away, right? Go away, you. Now this is our system. Would it work?
It should work.
Yeah, in theory it should, right? Here's what happens in practice when I do it. It doesn't work. Okay, that wasn't very explicit, was it? What happens is, how can I explain this? So, imagine that this is the space of all possible valid states through which you can pass, right? In fact, this is the space of all possible valid states through which you can pass. And there's nowhere in this space that is invalid, right? Like, where do I go if I want to make the ball fly off of the boom? And the cable turn sideways, and the boom turn wiggly, and Pokemon appear in the background. There's nowhere in this space that represents that, because all I've got are horizontal yaw and vertical cable length here to work with. And because there are only 2 degrees of freedom in my state space, I can't really do messed up wrong stuff. Now, let's suppose we had just one superfluous dimension, such that now this is our space of, I don't know why I deleted that segment. Anyway, we have some kind of a cube, and this is our space of all possible, let's put it back, all possible states through which we could pass. Yet we know that as we trade the system, it really only passed through 2 degrees of freedom of space. I don't know the right way to communicate that, but I think you'll agree with me that as the system ran, there must somehow in this be a 2-dimensional something or other. I'll just call this the manifold of what really happened. And as we wandered through our state space, we must have always been visiting points on this manifold within the higher space that we could have sampled, right? Well, what's that point? It's whatever, it depends on how the neural network generalizes. So, you know, if you've got that state, well, I guess in this case, if we went this far, then it's the image itself. Let's suppose we're just going to go down to 3 dimensions. So we represented the state in 3 dimensions, even though the system only passed through 2 dimensions. This is no longer identity, it's a complex thing. Well, if you go off to this point up here, that's some point that's off the manifold, then it does weirdness. It does whatever the neural network does, and it could very well be things like the ball disconnecting from the chain, or the boom bending, or whatever the neural network thinks it needs to do up there, because there are 0 training points constraining it. Well, so I think just to swing back to a point I've tried to make over and over throughout the semester, when you guess, when something is unconstrained, it's always wrong, right? And that's not that that's some kind of fundamental truth. It's that if you have no basis for being right, what are the odds? There are so many possibilities that it's irrational to think you have any basis for being right if you have no basis for being right. And if you're guessing, you might as well be wrong, because if you know you're wrong, then you know what the right thing is. So it's always wrong to guess, even if you might be right. Does that make any sense? Okay, well, this point out here is something we have never constrained our model to. Therefore, whatever we get, it's a blatant guess. It's not based on any generalizing principles. As we approach this type of a situation where, what am I doing? As we approach this type of a situation where the system has as much space to work with as the image, how many things could you represent in an image? Well, anything in the universe, right? I mean, you could have a picture of a unicorn dancing on a marshmallow with a bear that likes tacos, or whatever you want is in there somewhere. And so the burden on this transition function becomes one of two things. Not only predict how your state is going to be accurately, but don't screw up at all. Because if you screw up just a little tiny itty bitty bit, then you're slightly off of the manifold of valid states. And if you're off by just a little bit, and then you predict a little bit farther into the future, what happens? Now you're off even more, right? Do you know what chaos is? Chaos. So the chaos is often represented by the statement, if a butterfly in Brazil flaps its wings, can it cause a tornado in Texas? You ever heard anything like that? There's about 50 variants of it, so I'm sure I got it wrong. But here's the deal. A guy named Lawrence, I don't know how to pronounce it, was studying weather patterns. And he found, in fact, let's get a picture here. Lawrence, let's see what Wikipedia says for that.